Okay, hello, this is Hannah Bond, and this is my webcast following the week 6 class. First of all, I apologize. I have kind of run out of time, and so I do not have any interesting pictures to show this week. But anyway, for this week, I decided to go back and review the teacher notes for the electric charge and field model and for the electric potential model and the things that we've done in our class so far. The reason I'm going back at this point to review is I want to plan for how I'm going to cover these topics in my conceptual physics classes starting in a couple of weeks. These are my classes for students who are not very strong in math and science, so that I need to provide good support for any math beyond an Algebra 1 type skill level. And I'm going to begin teaching electric charge to them the first week in April. So I plan to begin with the demonstration of charging balloons. I'll blow up 4 balloons. I'll hang 2 of them from the ceiling. So first, I'll lay one on, put one resting on a desk, and we'll do a force diagram of it. And then we're going to charge that balloons. My students are all girls. They have a lot of hair, so it's not really difficult to find somebody to volunteer to charge the balloon, and we'll be able to stick it to the whiteboard, and then we'll talk about how we would do a force diagram for it while it's hanging there on the whiteboard, not moving. From middle school, most of my students are familiar enough with charge to understand that there's a positive and negative form of charge, and that negatively charged electrons are the things that move when you rub 2 things together. But we'll go through that discussion again, and we'll give a name to this new force. We'll call it the electrostatic force. Next, we'll work with the hanging balloons. We'll charge one of them and observe how it attracts the other neutral hanging balloon. And from that, we'll talk about how electrostatic force can be a force of attraction because we see the balloons moving together. Then we'll charge the second hanging balloon, and we'll observe that now the 2 balloons repel each other. So electrostatic force can also be a force of repulsion. And this experiment will also, or this demonstration will also show us that no contact is required for the force to act. Although this demonstration really just shows that charges repelling and just shows like charges repelling and a charged object attracting a neutral object, my students always bring out their prior knowledge that opposite charges attract and like charges repel. As a reinforcement of the things we discussed in class, I'll have the students run the University of Colorado Physlit on balloons and static electricity, and they'll answer some questions and draw some pictures from that for homework. Okay. Now, in the last couple of years, I have been reluctant to try the sticky tape activity in my class. But now that I've done that activity twice as part of our online class, I'm going to do it in this conceptual physics class. I've made my own version of the lab handout to kind of clarify some of the instructions, and my goal is to complete this activity in the same class period as the balloon demonstration. So it will immediately follow that balloon demonstration. Some of the important observations will be that 2 neutral objects, for example, the strips of paper, the strips of aluminum foil, don't interact with each other. So charge is required for there to be an interaction. Then we'll see that 2 like charged objects, for example, 2 top tapes, will repel each other. So like charges exert a repulsive force on each other. Then we'll observe that 2 unlike charged objects, for example, the top and bottom tapes, will attract each other. So unlike charges exert an attractive force on each other. The amount of interaction is stronger when the tapes are closer together and weaker when they're further apart. So there's an inverse relationship with the distance. Then we'll discuss how the charge is created on the top and bottom tapes. One tape becomes negatively charged by pulling electrons from the other tape. The tape that lost electrons becomes positively charged. Both tapes should have equal but opposite charges if we ensured that the original configuration of the two tapes stuck together was electrically neutral. We'll review the structure of an atom. That's something that we're talking about in the unit before this, so it will be fresh in the student's mind. And we'll discuss why only electrons can move between objects, while protons are tied to their nucleus. And we'll discuss how different types of materials have stronger bonds with their electrons. In metals and other conductors, electrons can usually move quite freely, and so we'll draw them with the electrons separate from the positive ions that they left. But in paper and other insulator-type materials, electrons are bound quite tightly to their individual atoms. The electron cloud might shift, but the electron doesn't leave the atom. And we'll draw these types of materials with the positive and negative charges inside the same circle representing the atom. Based on agreeing to assign the label of negative to the plastic comb rubbed with fur, we'll be able to identify that the bottom tape has a negative charge while the top tape has a positive charge. And so we'll be able to use that going forward as a way to identify types of charges. And then finally, we'll talk about how a charged object, either the top or the bottom tape, attracts a neutral object. And that will lead into a discussion of how polarization occurs, how the charged object can polarize a neutral object, which induces a localized charge. I'm still uncertain about whether I could successfully do the electrophorus activity having my class conduct that as team activities. I did the activity a few weeks ago as part of our online class, and so now I have the neon bulbs that I need for it, and it worked well for me. The only thing was that I really needed to dim the lights to see the light bulb light up. It was kind of a subtle effect, and I think it might be hard to duplicate with my girls working in teams. My classes are very small. I have 8 in one class, 9 students in another, and so I think I'm going to do this electrophorus as a group activity and discussion. This will be a good chance to use what we've just learned about sticky tape to identify that the styrofoam plate acquires a negative charge when we rub it on someone's hair, and we'll be able to tell that because it will attract the positive top tape and it will repel the negatively charged bottom tape. Also, this activity will be another chance to apply the things we've learned about how a charge can be induced in a neutral object when it's brought near a charged object, and also how the metal pie plate is a conductor so that its electrons are able to freely move. So first, we'll sketch the charges on the styrofoam and aluminum plates in 3 stages. First would be when the aluminum pie plate is brought near the negatively charged styrofoam plate and induces a charge. The second will be when the finger touches the neon bulb, allowing electrons to flow through the bulb, causing it to light up. And then the third will be when the aluminum pie plate now has a net positive charge, and the styrofoam plate still has a net negative charge at the end. And we'll use the sticky tapes to confirm the charges on the plates at this point. Then we'll do the next step of the demonstration. We'll raise the now positively charged aluminum plate in the air. We'll touch the bulb again. We'll see that the bulb lights up as electrons flow in the reverse direction back into the plate. And we'll use sticky tapes. We won't use sticky tapes. We'll now confirm that the pie plate is neutral by demonstrating that it doesn't interact with a neutral strip of foil or a strip of paper. Okay, so after that electrophorus activity, the next thing we'll do will be the conductors and insulators activity using the Van der Graaf generator and completing worksheet 2. I did this activity in my classes last year. It worked great as a way to emphasize this model of matter being comprised of microscopic charged particles and giving students a way to explain how different types of materials become charged. After that, the next thing that we'll do in the class, I'm not going to do a physical experiment using balloons and pith balls to derive Coulomb's law. Instead, I'm going to use the Coulomb's law gizmo on the www.explorelearning.com website. This simulator gives a repeatable experience. It's a good way for the girls to derive this relationship for electrostatic force as being proportional to the product of the two charges and inversely proportional to the square of the distance between them. And then following that activity, we'll do something similar to worksheet number 3 in class, and then there will be a homework assignment for some independent practice applying Coulomb's law. Okay, so now we'll be ready to start discussing electric field. A couple of weeks ago, I tried the new activity in the AMTA materials, trying to map the electric field using a sticky tape compass. I did not get good results, maybe because the humidity around Nashville is just too much to do that activity. So I'm going to use the charges and fields FET from the University of Colorado and worksheet 4A to talk about electric field. Using that FET, we'll talk about how electric fields always point away from positive charges and point toward negative charges. How they always begin on a positive charge and end on a negative charge. And if there are two charges, how the net field is the sum of the two individual electric fields. We'll also talk about how the field strength is inversely proportional to the square of the distance away from a point charge, but it's directly proportional to the amount of charge on that point charge. And that if you follow two adjoining field lines, when they are close together, the electric field is stronger at that location. When the field lines are further apart, the electric field is weaker. And then we'll demonstrate how the electric field vector is tangent to the electric field line. Let's see. Oh, and we'll also, I guess, talk about parallel plates and how that the electric field strength is constant between oppositely charged parallel plates, and that if the parallel plates are close, the field is strong between the plates and weak on the outside of the plates. Using this simulation, I'll have the students derive the equation for how to calculate the strength of the electric field due to a point charge. In one experiment, they'll find that field strength is proportional to the size of the charge. In another experiment, they'll find that the field strength is proportional to the inverse square of the distance away from the point charge. And so when we pull those two relationships into one equation, we'll get that the field strength equals kq over r squared. And then finally, in this unit, I'll have a worksheet in class where we'll solve some quantitative problems involving electric field, and I'll follow that up with a homework assignment for some independent practice. We'll do some review, and then we'll be ready for a test in this unit. So anyway, so I just wanted to spend this time this week going back and reviewing those things that we had done, because I want to go ahead and start applying some of the things we're talking about in class in my classes this spring, and that way if there may still be opportunity if I run into hurdles to ask you some questions. Okay, thank you.